chosen these two questions to do with you. The first one is on proportionality intercept theorem, and then the second one involves similarity and that kind of stuff. So those are our sort of two most important metric concepts. So those are the things that I'm going to be focusing on. Okay, so both of these are exam questions. The first one came out of a November 2014, but this is something that does get asked, especially where they ask you to calculate the area of one triangle over the area of another triangle. So I want to do these questions with you. All right, so the first thing that they tell us is that ABCD is a parallelogram. Okay, so that's going to become important to us. We need to make sure that we know all the properties of parallelograms. So for example, the opposite angles are equal in size, or the opposite sides are equal in length, etc., because all of these characteristics and properties of parallelogram are going to be important to us in order to be able to answer the question. They've told us the diagonals intersect at M. Okay, so now they're talking about the diagonals. What do we know about the diagonals of a parallelogram? What can you guys tell me about the diagonals of a parallelogram? They don't necessarily intersect at 90 degrees, Diana. That's it, Pam. They bisect each other. Absolutely, they bisect each other. Okay, not bisect the chord. Okay, remember chords are in circles, okay? But yes, they bisect each other. Okay, so in other words, they cut each other in half. All right, so now, Diana, what you're thinking about when the diagonals intersect at 90 degrees, then the parallelogram is a rhombus. Okay, so very, that's it, Kamchelo. Bisect equal angles. Again, that's a rhombus. A rhombus, the diagonals will bisect the corner angles. In a parallelogram, that is not true. Okay, so very important, make sure that you've learned the properties of parallelograms and etc., so that you know, well, not that you know, but I mean, so that you're able to answer these questions, okay? Because knowing those properties are what's going to help you be able to do the question. All right, so here they say to us that F is a point on AD such that AF is to FD is 4:3. So of course we all say, okay, well, that means I've got to do this. So it's 4:3, like so. And E is a point on EF. Sorry, E is a point on AM such that EF is parallel to BD. Okay, lovely. FC and MD intersect at G. Fine, we've got it. And now they want us to calculate, given reasons, the value of the following. Okay, so there we can see the marks. This first one is out of 3. So EM over AM. EM over AM. So of course, the first thing that we're going to do is go to the diagram and we're going to look at EM and we're going to look at AM. All right, so when we look at EM, we see that it's here. And when we look at AM, we can see that it's there. Okay, so they want you to work in a triangle. They are giving you the sides, and they're giving you the pieces of the sides that lie between the parallel lines. Okay, so in other words, what they want you to do is they want you to make a proportion in order to answer this question. Okay, and then obviously we have to provide a reason as well. This is proportionality, quite right, intercausal, quite right. Okay, so what is EM over AM equal to? What is EM over AM equal to? Which triangle are we working in? Okay, so intercausal says, is it AF over FD? You've got the correct sides, well, one of the correct sides, but you're not in the right order. Okay, triangle AMD, yes, perfect. So, yeah. But look at what they gave you guys, right? They gave you EM over AM. So that's the little side. over the long side. Okay, that's the little side over the long side. So EM over AM is equal to FD over AD. FD over AD. Does that make sense to everybody? Okay, so the shorter side over the whole side. Okay, and then here we would have to say proportionality intercept theorem. Remember, when we say proportionality intercept theorem, we have to name the parallel lines, otherwise we don't get a mark for the reason. So EF parallel to MD, and then that was going to be equal to, somebody already told us it was 3/7. Okay, that's it, lovely, that's fine, and of course you swapped it around, never mind. Okay, so there you can see your 3 marks. 1 mark for that, 1 mark for the reason, and 1 mark for the answer. Okay, so very, very important. When we use proportionality intercept theorem as a reason, we have to remember to name the parallel lines. Okay, just like if we use corresponding angles or alternate angles or co-interior angles, we have to name the parallel lines. Okay, they're going to be very, very strict with that in your final exams. They are not going to be forgiving if you leave the parallel lines off. So make sure that you write them. Okay, now we go back and we look at the question. The next question, CM over ME. CM over ME. So here is CM. I'm going to highlight it in a different color. There's CM. And then ME is the green bit. So CM over ME. And again, I think this was out of 3 marks. Let's just go and have a quick squeeze. Yes, also out of 3 marks as well. CM over ME. Now, at this point, it's easy to go wrong, because normally when we work with proportionality intercept theorem, we identify the sides that they're talking about. And then our next step is to look at the triangle that we're working in. Now, in this case, you may be forgiven for thinking that you work in triangle CEF, but you don't. You can't. Why can you not work in triangle CEF to answer this question? Why will that not work? No, there's 2 parallel lines. There's 2 parallel lines. You've got a parallel line MG and another one EF. But applying the proportionality intercept theorem in that triangle does not help you. Okay, why does it? That's okay. That's okay. Why doesn't it help you? I'm just putting over here that that was 4:3 as well. So I mean, if that's, say, 3x, then that would be 4y and 3y. Okay, so the reason that we can't work in triangle CEF, okay, is because there isn't enough information. Hello, Bridget. So nice to have you with us. Thank you for joining. Okay, you don't have enough information. Okay, so you don't know anything about the length of CG and GF. So working in that triangle in this situation is not going to help you at all. Yes, Katlwano, go for it. You're welcome to unmute and ask. Why did I add the X and the Y? Okay, because those sides are not the same length, Katlwano. Okay, they are in the same proportions, but they are not exactly the same length. Okay, so that's why we can use different letters to represent the lengths of the line. So even though they're in the same ratio, they're not actually the same length. Okay, you don't have to use letters. It's something that you may have seen your teacher do, or then again, you may not have seen your teacher do. Okay, so whether you use them or not, it doesn't matter. Okay. So now we've got to figure out another way to be able to answer this question. And this is where, no problem. And this is where I was going on about the properties of parallelograms are so important. Okay, remember, M is the midpoint of AC. Okay, so line BD cuts line AC in half. So AM equals MC is what I'm trying to get at. So if AM equals MC, we already know what ME is. We already know that it's 3. How long does CM have to be? Exactly, Zafika. Exactly, Kanisa. Quite right. Okay, but remember, this is geometry, so we can't just write down answers. We've got to explain why we say the things that we do. So we need to state here that CM is equal to 7. Okay, and our reason, the diagonals of a palm bisect each other. Okay, and that's why CM over ME is going to be equal to 7 over 3. Okay, so again, it's out of 3 marks, 1 mark there, 1 mark there, and another mark there. Okay, everybody good? This is making sense. Are you all happy? You can send us an emoji. Good, Safika. Everybody else all right? Making sense? Cool. Cool. All good. Awesome. Oh, you guys are amazing. Thank you. Okay, lovely. All right, so now that we've managed to do those two, let's go and have a look at question 1.3. So yeah, something that does come up on a regular basis. They want us to calculate the area of one triangle over the area of another. So what I'm going to do now is I'm going to erase everything that I've got here, okay? And I'm going to highlight the triangles. Okay, so FDC is this guy over here. There's FDC. And BDC is this guy here. Okay, so those are the two triangles that we are working in. So they want us to put the area of the one over the area of the other. All right, so now, you know, now that you're in matric, there are 2 ways that you could work out the area of a triangle. What are the 2 ways you can work out area of a triangle? Tell me what they are. I'm just going to turn my light on while you guys answer that question. How do we work out the area of a triangle? There's 2 ways. By the time we get to matric, we know of 2 ways that it can be done. Yeah, half base times height is correct. The cosine rule? The area rule, that's it, the area rule. Okay, so the cosine rule is used to calculate an angle or a side. Okay, you can't calculate the area of a triangle with the cosine rule. You can work out a missing side, or you can work out the size of an angle, but you can't calculate the area. But you're right, it is, it's the area rule. No problem, intercourse, don't say sorry. No reason to say sorry. Okay, absolutely. So when they ask you a question like this, you are either going to have to do it by half base times height, or you're going to have to do it by the area rule. Okay, it's the only way that you can work out the area of a triangle. Now, if they want you to use the area rule, there has to be an angle that is in common. Okay, so they have to share an angle. So for example, if I draw a triangle like this, let's say there's my triangle, and let's say over here I've got a pair of parallel lines, and now that's A, B, C, D, E, and now they say to us the area of ABC, triangle ABC, over the area of triangle ADE. Now, I would use the area rule in this case, because if you have a look here, angle A is common. Okay, so it's in ADE and it's also in ABC. Then I'm going to use the area rule because both triangles contain or share this angle A. If we have a look at the diagram, right, that I've highlighted for you, the yellow triangle and the blue triangle, do they share an angle like triangle ABC and ADE? Do they share an angle? But is it the same size? I mean, it's part of C. Triangle FDC has part of angle C. It doesn't have the whole thing. So can I say that it's common? Okay, so Kanisa says D, Bridget says D, Specicle, you're saying A. A isn't in either triangle, unfortunately, Specicle. Lauren says G. Okay. So G is not an angle in either triangle. Safika says, okay. Now, unfortunately, guys, that is not true, okay? Triangle FDC and DBC do not share an angle. They might share parts of an angle with one another, but they don't share an angle in the same way that triangle ABC and ADE do. Okay, it's got to be a whole angle. Okay, that's got to be the same. Here, it's part of D and part of C, not the whole of D or the whole of C. Can you guys see that? Okay, so they don't share an angle. They share parts of an angle, but they do not share a whole angle. Fahim, you had your hand up. Do you want to ask a question?
No, ma'am.
Okay. All right, that's fine. Okay, so sharing part of an angle is not enough. Okay, it's got to be the whole angle if you want to use the area rule. Okay, otherwise it's not going to cancel. Okay, it has to be a full angle, Camgelo, the same angle. Doesn't matter which angle it is, any one of the three is okay, but it has to be exactly the same size. So angle D in triangle DBC is not the same size as angle D in triangle FDC. Can you see that? Okay, so angle D in triangle DBC is smaller than angle D in triangle FDC. Can you see that, Matrix? Okay, and similarly, angle C in FDC is smaller than angle C in triangle DBC. Okay, so C in the one and C in the other are not the same, and D in the one and D in the other are not identical. Okay, so we cannot use the area rule because there is no common angle. Okay, so that means it has to be half base times height. All right, and this is again where, does that make sense to everybody? Okay. You never saw that until now. Oh, I'm so glad. I'm so glad that you can see that. Now, the other thing that we need to remember here, what's important here, is that these two triangles lie between the same parallel lines. Okay, they lie between, both triangles lie between AD and BC. Right, so now, well, what do we know about parallel lines? We know that lines are considered to be parallel when the distance between them never changes. That's why the lines can't touch each other, because the distance between them never changes. All right, so that's why they will always run next to each other without touching. So because the distance between them is the same, we will say that when it comes to triangles lying between parallel lines, they have the same perpendicular height. Okay, so what I'm going to do is I'm going to draw a line in red from the base of triangle FDC, which is line FD, to the base of triangle DBC, which is BC. Can you see they have the same perpendicular height? Right, so that's perpendicular here, and that's perpendicular there. They have the same perpendicular height. Do you see that? All right. Everybody cool with that? Good. All right. So now, when we talk about the area, just reading everything that you guys are written. Okay, lovely. So now when we talk about the area of a triangle, half base times height, remember base times height, those two sides, the base and the height, have to be perpendicular to one another. Okay, when we're working with the area rule, we can apply the area rule to triangles that are not right angled. But when we are talking about half base times height, it doesn't necessarily need to be a right angled triangle, but the base and the height have to be perpendicular to one another. So if I call this red line H the height, you can see that it is perpendicular to the blue triangle's base, which is BC, and you can see that it is perpendicular to the yellow triangle's base, which is FD. All right, so they share the same perpendicular height. Sure, intercausal. So in other words, intercausal, when lines are parallel, the distance between them remains constant. So the distance between AD and BC is the same for both triangles. Okay, because if we consider FD the base of the yellow triangle, then C lies on the same horizontal as the perpendicular height. And if we consider BC the base of triangle DBC, we can see that its vertex is in line with line AD as well. Okay, so the red line represents the perpendicular height of both triangles. Okay, so in other words, if we've now got a base, we've now got a perpendicular up to the vertex. Does that make sense to you? Okay. So in other words, when we talk about the area, so this is 1.3. So when we talk about the area of FDC, we're talking about half the base is FD times the perpendicular height, which we've called H. And when it comes to triangle BDC, we've got half and the base is BC and the perpendicular height is H as well. Does that make sense to everybody? Are we all good with that? Lovely. Good job. Okay, very nice. And now we can cancel. Okay, because remember, oh, I'm so glad. Okay, so now remember, anything divided by itself is 1, isn't it? So a half divided by a half is 1, and H divided by H is 1. Okay, so what we are left with, matrix, where's my pen? Where's it gone? All right, down a little bit. Oh, it's up there. Okay, so what we are left with is FD over BC. Okay, and now we can go and fill in what those values are. All right, we know what FD is. Unfortunately, I've rubbed it off. Remember, this was 4:3. Okay, and BC, remember the opposite sides of a parallelogram are equal. AD equals BC. Okay, so I need to put that in here. AD equals BC. Opposite sides of a palm are equal. Okay, so FD was 3 and BC was 7. Okay, everybody happy with that? Good stuff. Lovely. Awesome. Okay, that makes me very happy. Okay. Lovely, lovely, lovely. Okay. All right, so now let's go and have a look at the next question. Okay, and I chose this one on purpose because it is a little bit more difficult. And I think it is also the sort of thing that is a very common sort of exam type question, you know, especially the part where they say write down with reasons 3 other angles each equal to x and prove with reasons. And then here, what's nice about this question is that they have included grade 11 circle geometry together with the grade 12 work. Okay, so you can see here, this was out of 25. That's a lot of marks. So 6 marks for 3 reasons. So there would be a mark for the angle that's equal to x and the reason why. So 1, 2, 3, 4, 5, 6, statement, reason, statement, reason, statement, reason. And then proving that WSTV is a cyclic quad, that's only out of 2. So that's not as difficult. Then we need to prove that a triangle is isosceles, that's out of 4. Then we need to prove that triangles are similar, that's out of 3. That's also quite a normal question to be asked. And then the last one is going to be the difficult question. Okay, so if you can make sure that you can do the 6 and the 2 and maybe even this 3-mark question over here, then at least you've got 50% of the question. Okay, so if there's something that throws you, remember, do not get upset by it. Okay, you don't have to get every single question right in order to pass, but you've got to be able to do the level 1 and the level 2 stuff, which is what number 1.1 is. Okay, so first things first, with geometry, we always read the question, we look at the questions, we look at how many marks it's out of, because that gives us an idea as to how much working is required. All right, so in the diagram, it says that S, T, and VT are tangents to the circle, and S and V respectively. So what does that mean straight away for us? If T is a common point, what can we say about ST and TV? What can we say about ST and TV? Okay, absolutely, they're equal, quite right, quite right. Right, what's the reason that they're equal? Do you remember the reason? Why is ST and VT equal? They are equal, Kamchela. Why? There we go. Causal tangents from a common point. Lovely. Itumeleng, it's tangents from a common point. Okay, not angles. That's it, Diana. Okay, tangents from the same point. Good, lovely, well done. 100%. Okay, so that's, you're going to see that's going to become important to us later on as well, because now we've got 2 sides that are equal. Lovely, lovely, Kamchela, perfect. All right, so we know that they're equal to one another. R is a point on the circle. We can see it down there. What else have they told us? And W is a point on chord RS. So it's a chord. We don't know that it's a diameter. They just said that it's a chord, such that WT is parallel to RV. So the minute we see that there are parallel lines, what do we start thinking about? What do we think about when we see parallel lines? What sort of angles? That's it. Absolutely, our fun angles. So corresponding, alternate, and maybe even co-interior. Yes, absolutely. And what are we not going to forget to do? Name our parallel lines if we use any of the fun angles. Okay, very, very important. Then they say to us that SV and WV are drawn. WT intersects SV at K, and they've said let S2 equal X. All right, so now that angle S2 happens to be an angle between a tangent and a chord. Okay, so the tangent is ST and the chord is SV. All right, so straight away, the angle between the tangent and the chord is equal to an angle in the alternate segment, right? So now what I want you to do, if possible, is put your finger at S and your finger at V, okay? Remember, angle X or angle S2 is the angle between the chord and the tangent. The tangent is ST, the chord is SV. All right, and now what you're going to do from SV is you're going to follow the lines to the circle. Okay, what angle is sitting at the circle? Angle? That's it, intercausal, angle R. Can the rest of you see this? Okay, that's it, angle R. Angle R is sitting at the circle. Okay, so in other words, the angle between, so now listen to the words and look at what I'm highlighting, okay? The angle between the tangent and the chord, which I'm drawing very badly, and the chord is equal to the angle in the, follow S and V to the circle, is equal to the angle in the alternate segment. All right, so that would be R. Okay, so S2 equals R. R is also equal to X. All right, that's what I'm trying to say. Erase that. Okay, so our first thing here that they wanted us to do is write down with reasons 3 other angles each equal to X. So the first angle that we can see that equals X is R. R equals X. And our reason, tan chord theorem. Okay, everybody good with that? Sure. Okay, so Kutsu, you want me to repeat? It's fine. Kaugelo, you want me to repeat? Not a problem. Is V3 also not equal to X? Okay, Diana, you are right. V3 is equal to X, but it's not because of tangents from the same point. Okay, so you've got to be careful about what reasons you use here. What we would do is we would say that ST equals VT, tangents from the same point. But V3 equals X because of angles opposite equal sides. Okay, so the correct reason is angles opposite equal sides. But yes, Diana, you're quite right. Okay, so Kutsu, what I was trying to get you to do here, right, was I was trying to get you to use tan chord theorem. Okay, angle S2 is the angle between the tangent being line ST, and the chord being line SV. Okay, so this line over here. Right, and then I wanted you to put your fingers at S and at V, and then follow, so one finger at S, one finger at V, and then follow it to the circle. Okay, and that helps you to identify the angle in the alternate segment. Okay, which in this case is R. Okay, so the angle between the tangent and the chord is equal to the angle in the alternate segment. Okay, now, as Diana was saying, V3 is also equal to X, but the correct thing to say here is this: ST equals TV, tangents from the same point. Okay, which is something you guys have already identified. So therefore, V3 equals X because of angles opposite equal sides. Okay, good. Oh, good. I'm glad. All right, so let's place here. And now we can put in our X's. All right, so we're nearly there, guys. We've got V3 that is equal to X, and we've also got, now that you've got those angles that are equal to X, what are they also equal to in the diagram? Is there something that V3 equals in the diagram? Is there something that W3 equals in the diagram? So now we've got to go from R and V3 to other angles that could be equal. Okay, what do you think? What else does V3 equal, what else does R equal? Ah, okay. So there we go, Kutlwano. Lovely. Okay, everybody look at what Kutlwano said. Okay, W3 is equal to R because they are corresponding. Okay, W2 equals V1. We don't know how big V1 is because of alternate angles. But look here, look at the corresponding angles. Can you see the F? I'm going to draw it for you. Okay, so there is the backbone of the F. There is one arm and there's the other arm. Okay, can you see the W3 and R correspond? Diana, you're quite right. S2 and W2 does make a bow. All right. It does, you're quite right. But we don't know that WSTV is cyclic. Okay, so we can't say that W2 equals S2 because of angles in the same segment. Okay, right. But that's one of the things that we're going to have to do, okay? It's one of the things that we're going to have to do. Okay, cool. All right, so there we go. So that was the first one was R. The second one was V3. And the third one, who was it that did that third one so well? It was very nice. Well done. Okay, so now W3 equals, and I'm using corresponding angles. I must name the parallel lines. Okay, so RV parallel to WT. Okay, and now you've got 6 out of 6. Statement, reason. Statement, reason. Statement, reason. Okay. I wonder if other people, am I breaking up to other people as well? Nelly, am I breaking up a lot? Am I? Okay, well, I've got a fiber connection. Wi-Fi shouldn't be breaking up. Sorry. Sorry, guys. If you miss anything that I say, so yeah, if there's anything that I say that you miss, then tell me and I will repeat myself. No problem. Now, maybe it's network, I don't know. Okay, so there we go. We've done 1.1. Now we need to move on and do 1.2. So they want us to prove, I'm echoing too much. I don't know why that is. There's only one of me. There should be an echo. I don't know what to do about this, guys. Neliswa? Am I echoing? Nelly? Am I echoing?
I think now it's fine. It sounds fine now.
Is it better now? Okay, all right.
Yes.
Okay. All right, let's carry on with the question. All right, so now they want us to prove with reasons that WSTV is a cyclic quad. All right, so you're allowed to highlight in your question paper. You're not allowed to highlight in your answer book, but you're allowed to highlight in your question paper. So WSTV, I'm going to highlight. Now remember, this is only out of 2 marks, okay? So it cannot be something that is particularly difficult or strenuous if it's only out of 2. Remember, geometry is a story. We use what we have, okay? So we know that when there is a bow tie inside a cyclic quad, we can prove the quad is cyclic using converse angles in the same segment. Okay, so now what I want you to do is this. Put your fingers at S and T. So from S and T, go to W3, then go back to S and back to T, and from S and T, go to V3, and then go back to ST. Can you see that? So from S and T to W3, go back to S and T, from S and T to V3. Can you see that both V3 and W3 equal X? Can you see that? Okay, and that's why WSTV is a cyclic quad. Okay, because W3 equals V3. All right, so now we just need to put that down on paper. Okay, so in 1.2a, we can say that W3 equals V3. Okay, remember it came from here, W3 and V3. Okay, they're equal to each other because they both equal X. Therefore, WSTV is cyclic, and our reason, converse angles in the same segment. Okay. Are those angles in the same segment? Yes. Okay. So it's converse angles in the same segment. Because the angles in the same segment are equal, that makes WSTV a cyclic quad. Okay, everybody happy with that? Are we all good, guys? Okay, so intercausal, it's converse because you are proving that the quad is cyclic. Okay, so when you prove that a quad is cyclic, I don't know what your teachers have taught you guys at school. There are other things that you can say, but because at my school, what I always do is I teach angles in the same segment and then converse angles in the same segment. And then I teach opposite angles of a cyclic quad are supplementary. So the converse is converse opposite angles of a cyclic quad are supplementary. Okay. And then I teach exterior angle of a cyclic quad and then converse exterior angle of a cyclic quad to prove that the cyclic quad is, to prove that a quad is cyclic. Okay, and then it's only one thing you have to remember instead of another set of rules. Okay, so when you are proving a quad is cyclic, it's always converse. So either converse angles in the same segment, converse opposite angles are supplementary, or converse exterior angle of cyclic quad. Okay, lovely. Okay, good stuff. All right, now they want us to prove the triangle WRV is isosceles. So I'm just going to highlight triangle WRV. Here it is. And they want us to prove that it's isosceles. What does that mean? They want us to prove it's isosceles. What are they essentially telling us we need to do? There we go, exactly. So they want us to prove that there are two sides that are equal to one another in length. And if there are two sides that are equal to one another in length, it's because there were two angles that were equal to one another in size. Now you already know that R is equal to X. Okay, so in other words, either we need to prove that W1 equals X, or we need to prove that V1 equals X in order to do this. Okay, so either angle W1 or angle V1. We need to prove that either one of those two is equal to X. So now looking at the diagram, you've just proved that the quad is cyclic. So you can work with angles in the same segment. What connections do you see? Either W1 is X or V1 is X. Which one and why? Okay, so exterior angle of a cyclic quad is equal to the opposite interior angle. So W1 would be equal to angle STV, but we don't know anything about angle T. How big is W2? What is W2 equal to? Because the quad is cyclic. Because WSTV is a cyclic quad, what does W2 equal? Exactly, it equals X, 100%, lovely. Okay, so because of angles in the same segment, all right, so in other words, this angle X over here, this one is also equal to X. Okay, angles in the same segment. Lovely. And now we've got our parallel lines. Remember our fun angles. Okay, so we've got our parallel lines that goes from here, which is that angle X over there, and then that angle over there. Can you see what I'm trying to show you here? Okay, we've got a Z. All right, so this angle V1 is also equal to X because of alternate angles. Okay, can you see that? Okay, so V1 is also equal to X because it is alternate to W2. W2 is equal to X because there are angles in the same segment with S2. Okay, that's the connection. Okay, so now let's get it down on paper. That's it, alternate angles. Okay, so the first thing that we needed to say in part B was that W2 equals X. That's where our story begins. Angles in the same segment. Then we needed to conclude that V1 equals X because of alternate angles. Okay, so remember we've got to name the parallel lines, okay? So WT parallel to RV. So what this means is that angle R equals angle V1 because they both equal X. That means that WR equals WV because they are sides opposite equal angles. So that is what makes triangle WRV is isosceles. Okay, so this bit over here. Is that making sense to everybody? Good stuff. Oh, I'm glad. It's all good. Good. So I'm so pleased. All good, Bridget. Okay. All right, so now we're not going to have time to be able to finish this entire question because can you believe it? It's already 50 minutes are gone. It's unbelievable how fast the time goes. It's yeah, it is a little bit complicated. So WRV is this triangle over here, WRV. That's this one. And then triangle TSV. TSV. So let's just do this. So TSV is this one. Okay, so they want us to prove that those triangles are similar to one another. So I think I'm going to have time to do that, and I'm not going to have time to do anything else. All right, so very important is our set out here. What I'm going to do is I'm going to rub this off, and I'm just going to pop it on the screen in this space over here. Okay, so when we prove similarity, very important, we started off by naming the triangles we're working in. So in triangle WRV and triangle TSV. Okay. Well, here we've got an X, and here we've got an X, and here we've got an X, and here we've got an X. All right, so this is going to be pretty easy for us. What we can do is we can say that S2 equals R. Okay, both equal X. And in number 2 here, we can say that V3 equals V1. And again, because they both equal X. The third remaining angle is W1, and it is equal to angle STV. And that is because it is the third angle of a triangle, angle sum in triangle. Okay, so therefore, triangle WRV is similar to triangle TSV, angle, angle, angle. Okay, and that'll get us our 3 marks.